All right, everybody, welcome to lecture 11 of PH 870 quantum computation. Now, in the last class, we had talked about quantum teleportation. And I really like the fact that at the end of the class, you all had so many different questions that you asked me. And of course, I probably was not able to answer all the questions to everybody's satisfaction. But the bottom line is that what quantum teleportation achieves is it's a protocol for transferring an unknown quantum state from one observer to another observer using classical communication as the medium through which information is conveyed. Now, as almost a byproduct of the same setup, we are able to achieve something else, which is called superdense coding. So this I suppose will be our second application. Let's see. Okay. So what do we mean by superdense coding? And is the following. So again, we have, as usual, our protagonists, Alice and Bob, and they want to transmit some classical information. Okay, so Alice has two classical bits of information, and she wants to transmit these two bits to Bob. Okay. What superdense coding achieves is the following. Alice can transfer two cbits of information to Bob while sending only one cbit to Bob. All right. So what do we mean by coding is that, right, we want to take some data, we want to compress it, give it a more compact representation so that it costs us less in terms of resources to transmit it from one point to another point, right? And so coding by its very definition takes some data and converts, makes it dense, right? Increases the density of data. So, but of course, no coding that you can do would allow you to take n bits of information, right? N incompressible bits. This is the important part. And send them from one observer to another using less than n bits of information to transmit, some information to the second person. So these two bits, right, that Alice wants to transmit, they they form part of a incompressible message. Okay, so this is important, because it might be possible, it might be the situation that the message that Alice is sending in the form of these two bits could actually be compressed in the following way. So for instance, these are the two bits that Alice has, right? And you could have some compression scheme, right, which allows you to compress the message down into a single bit, right? So then Alice only needs a single bit, because the original data is compressible. Okay. Well, I mean, I suppose that's not strictly correct, because these two configurations are not the same. But if you don't care about which bit is 0 and which bit is 1, then they are. And in that case, Alice only needs one bit. Right? So the assumption here is that the two classical bits are incompressible. And another way of saying that is that the uh, two classical bits are uncorrelated, right? Because if they are correlated, then you can take the correlations and use those correlations to compress the information. This also tells you, by the way, that data which is maximally compressed, uh, if you look at the different components, you'll find that the correlations between the different components um, will be very small. So how does Alice achieve this? Well, as usual, we have to have EPR pairs. Okay, so we take an EPR pair, and once again, we can take any one of the four states. If you remember that there were four states that we had defined in the previous lecture for EPR pairs. Let me go and find that nomenclature, right? So this was the expression for the four different possible Bell states, right? Beta 0, 0, beta 1, beta 2, beta, well, there are four of them, right? So this is beta 0, 0. And what we want to do is we want to, again, take one bit. One of these bits goes to Alice. Okay. And the other bit goes to Bob. So let's say the first bit goes to Alice. First qubit, the first half of that EPR pair goes to Alice, and the second half goes to Bob. Right? Now, what does Alice do? So this is one qubit and this is one qubit, and they are in this entangled state. Okay. So the algorithm is the following. In order to, so Alice wants to send the message xy, where x and y are both belong to 0 and 1, right? So what does she do? She applies an operation, some operation u, which depends on these two bits that she wants to send to her copy of the qubit, to, let's say, psi a. And then she sends her state psi a, the modified state. She sends this qubit plus one classical bit. To Bob. Okay. Now, okay, yeah, my mistake, my mistake, my mistake. She doesn't need to send one classical bit. If she needed to send one classical bit, then well, we wouldn't really call this. So all she has to do is send one qubit to Bob. All right. So what does she do? So let's say she wants to send the message xy is equal to 0, 0. In that case, she does nothing to her qubit. It's just unchanged. It's just the identity. If she wants to send 0, 1, okay, where then what does she do? She applies the Z gate to her qubit. If she wants to send 1, 0, then she applies the X gate to her qubit. As she wants to send 1, 1, then she applies the gate IY. Okay. So what does the application of these gates do to the overall state of the system? Right. So to begin with, the global state of the system, the global state is the following, right? It's this Bell state, 0, 0 plus 1. The first qubit, the one on the left, is Alice's. So if she applies this operation, the first one, what happens? She sends it to Bob, and well, nothing, the global state is unchanged, right? What happens when she applies the Z gate to her qubit? Right now, what does the Z gate do? Z acting on 0 gives you 0, and Z acting on 1 gives you -1. So what happens to the global state of the system? The global state of the system becomes 0, 0, -1, 1. Okay. What about the other one? She applies an X gate to her qubit. So what does the X gate do? Right? It just flips her qubit. So what will happen? 0, 0 will become 1, 0, and 1, 1 will become 0, 1, right? So Alice's qubit, the leftmost qubit, has flipped. And if she applies IY, right? So Iy is the following. So let me just write them down again. This is Z, this is X, and then Y is this expression. And so if you write down I times Y, you get 0, 1, minus 1, 0. And this operation Iy can be written as a product of X and Z. One, 0, 0, minus 1. So if you multiply these out, you get 0, minus 1, 1, 0. Right? So there's a minus sign over here. So I believe that if you take ZX, you will get Iy, right? So if she applies Iy, what happens? Both the her qubit. So let's just apply Iy, right? So if you apply Iy to 0, what will it give you? It will give you minus 1. If you apply Iy to 1, it will give you 0. Okay. So we'll get 0, negative, minus 1, 0, and then plus 0, 1 by root 2. So these are the 4 possible results of the operation that Alice can perform on her qubit. Okay. Now she sends her qubit to Bob, right? Let's say she sends, we can pick any one of these states. Let me just pick the third one corresponding to the 1, 0, right? Let's say she sends this one to Bob, right? I mean, she's not really sending this state to Bob. She's sending her qubit to Bob, but her qubit and Bob's qubit together, they're globally in this state. Okay. Now, the thing is that Bob can perform a measurement of these 2 qubits, right? So, see.
Alexa, is she sending this through quantum teleportation?
No. She's just sending it classically. Like she's not. No, there's no teleportation involved. She's putting that qubit in a package and sending that package to Bob. Just a classical package. Of course, you have to ensure that that qubit does not interact with the environment. Okay. Now, Bob can make a measurement of the 2 qubits that he has received. Okay. Bob measures both qubits. And when he measures these 2 qubits in the Bell basis, he can determine that Alice has sent the message, in this case, 1, 0. Okay, so what is the Bell basis? First, let me explain what the Bell basis is. It's the following. Remember, for 2 qubits, we wrote down these were the basis states, right? This was the computational basis for 2 qubits. This was the computational basis, right? You can call them one with a tilde, let's say 3 and 4. Okay. So what is a Bell basis? Well, you know that you can take any linear combination of these states and get a new basis, right? So what linear combination do we take? We take the following linear combination. Right? So the linear combination that we take is precisely the 4 possible states that she can send to Bob. Okay, and if we go back uh, to the notation that uh, we had used the last time, the beta 00 and the beta 11. Let me just go to that. Where was that? Yeah, so this was the notation, right? So let me just copy and paste it for reference. Right? And so these states, these 4 states, this is what we call the Bell basis, right? So you have the original one, then the one with a negative, right? So this you get with the Z. If you act with the Z gate analysis qubit, if you act with the X gate analysis qubit, and if you act with the IY gate analysis, right? So this is the Bell basis. So what does Bob have to do now? Bob makes a measurement of these 2 qubits. Okay. And but the thing is that you can always make a measurement in any basis that you want, right? You can measure in any basis, right? As a very simple example, let's say that Alice has a single qubit, okay, and which she prepares in the 0 state. Then she sends it to Bob. Bob makes a measurement of the state of this qubit. But when Bob makes a measurement, what does he do? He uses a different basis. He uses a different basis. Let's say the basis that he uses is the plus minus state, where plus minus refers to the linear combination of these 2 states. Okay. So what will Bob find, right? Well, the state we are measuring is this one. So how will I write the 0 state as a in terms of Bob's basis, right? In terms of Bob's basis, I will write the 0 state as the plus state plus the minus state And um, will there be a factor of √2? I think probably a factor, right? So when Bob makes a measurement on Alice's qubit, what will the result be? Right? Bob will get plus 50% of the time and minus 50%. Now, this is very important to understand, right? Measurements, the result of a measurement depends on the basis in which you make that measurement, right? So, for instance, 0 and 1, these are eigenstates of which operator? Another way to say it is, it depends on which operator you measure. So these are eigenstates of the poly Z state, Z operator, right? What about plus and minus? These are eigenstates of what? These are eigenstate of the bit flip operator, right? The NOT gate. So both of these operators are Hermitian, right? So Bob can choose to measure, right? Oops. Any Hermitian operator that he wants, right? There is no restriction. So Alice prepares a state psi and sends that state to Bob. Not Bob. What does Bob do? Bob takes some operator and measures the expectation value of this operator in the state that Alice has sent. And what is this O? This O is any Hermitian operator, right? So for instance, if Alice sends psi, if Alice sends the 0 state, Bob chooses to measure the X operator. What are the eigenstates of the X operator? The eigenstates of the X operator are plus and minus, right? So what will be the result of this measurement? The result of this measurement, right, will be, there will be two possibilities. Bob will get either the plus state and what will be the probability of this? It will be the projection of the state Bob has received onto the plus eigenstate, and likewise for the minus one. Okay, so if Alice sends the 0 state, what will Bob find, right? So if psi is equal to 0, P plus will be 0.5 and P minus will be 0.5. But on the other hand, Alice could choose to send Bob a state which is one of the eigenstates of the X operator. In that case, what will Bob find? P plus will be 1 and P minus will be 0. Right? So is this aspect clear? I hope that. Yes, sir. If you don't understand something here, then please let me know. So what are we doing in this superdense coding? Oops. In superdense coding, what we are doing is we are starting with a Bell state. Our initial state of the system is beta 0, 0. Okay. And Alice applies an operation to the state, right, which converts it into beta xy, where xy corresponds to the classical message that Alice wants to send. These are two classical bits, right? What does Bob do? Bob makes a measurement in this beta xy basis. Okay. So in other words, Alice sends this thing. So what does Bob find, right? Bob finds, when Bob makes a measurement, there are four possibilities, right? What will be the different probabilities? The probabilities will be 1 and 3 zeros, right? So because what will be the various probabilities? The various probabilities will be beta 0, 0 psi, where psi is the state after Alice has applied this unitary operator, right? Then the other probability will be beta 0, 1, beta 1, 0, and beta 1, 1 psi squared, right? Because Bob is making a measurement in this basis. Now, what does Alice do? Alice is sending him exactly one of these basis states, right? So if psi is, let's say, beta 1, 0, what will happen? P0, 0, P0, 1, and P1, 1, these will all be 0. And P1, 0 will be equal to 1, right? And so then Bob will know with certainty, right, that Alice sent him the state corresponding to beta 1, 0, which means the message that she was trying to convey to Bob was 1, 0. Okay. So Alice has managed to communicate a message which contains two classical bits using a single qubit. So this is super dense coding. Okay. Are there any questions about this? If something is not clear, I mean, well, actually, I probably should talk about measurement. And I think when I talk about measurement, things will become a little bit more clear. Okay. So all of this depends on you being able to understand what is going on. For instance, when I talk about this operation here of measurement. Okay, so let me talk about that, because I think that may be a point of some confusion. Okay. Now, so let's look at an example of one measurement. Okay, let's take the Bell state beta 00. Okay, and let us measure some operator. Let us measure the following operator x1 z2. Okay, now first of all, a bit of notation. What does it mean when I say I'm measuring the operator x1 z2? The indices on the operator, they indicate that this will act on the first qubit and this will act on the second qubit. Okay, so if I want to be technical about it, the operator corresponding to this x1 z2 will be written as follows: x1 tensor identity right, and then multiplied by identity tensor z2. Okay, that is what the operator, when I write x1 z2, that is what this operator corresponds to. And so I can also write this as x1 tensor z2 just for short. Okay, and then one can ask, well, what is the expectation value of this operator in the given state, right? So the expectation value would be just me taking this operator and sandwiching it between two copies of this state, right? So now let me just take the operator and see what happens when I act on beta 00 with this. So when I take x1 tensor z2 and I act on this state 00 plus 11 by root 2, what will happen? Can somebody tell me what will happen to the 00 state under x1 z2? So let's just take x1 tensor z2 and act on 00. What will be the result? Ujjwal, can you tell me?
So 1 and 0.
Right. Who said
10?
Right.
Sir,
So this will be, so x1 will flip the first qubit and z2 will just give me 0. Right. So I'll get 1 0. And what about the second one? X1 will flip the second qubit and z2 will give me -1. Right. So this is the result of this operation. So now I can write down this expectation value. What is this expectation value going to be? It's going to be the inner product of the adjoint ket with the state that I get by acting upon with this operator x1 z2, right? And this is going to be 0 because these states are all orthogonal to each other, right? 0 0 is orthogonal to 1 0 and so on. Is this clear to everybody? Are there any questions? No? Okay. All right. So now let me talk a little bit about measurements in a little bit more of an abstract way. Okay. So let's see. Okay, so let me talk about projective measurements. And hopefully this will make clear what is happening in when Bob is doing this superdense coding, this measurement. Okay, so what are projective measurements? So remember that a projection operator has the following properties, right? It is equal to the its own square, right? So if you take any state in a Hilbert space and you construct the outer product of the state with itself, you get a projection operator, right? As long as it's a normalized state, because you can check quite trivially that if you take the inner product of this object with itself, you get the same state again, or the same object. And what does this do, right? I've talked about this previously, is that if you have an arbitrary state of your system, then you can write it in terms of two components, one which is parallel to your to some state, and one which is perpendicular to some state. So rather than this, let me write this as psi and psi perpendicular. So alpha is the component parallel to psi, right? So if I take p psi and I act on phi, right, what will I get? I will get psi, this thing acting on phi. The inner product of psi with the state perpendicular to it will be 0, right? And I will be left with alpha psi, right? So what does this projection do? It takes my state and removes everything except that component. Now, when we talk about measuring an operator, okay, so we have some Hermitian operator. Let's say we are making a measurement of this operator, right? What does that mean, and how can I relate that to projective measurements? O will have some set of eigenstates, right? And these eigenstates will form an orthogonal basis for my Hilbert space, right? So let's say I have some set of eigenstates which form an orthogonal basis. Okay, now what does it mean when I have some state psi and I want to measure the operator, when I want to measure the expectation value of psi? Or sorry, expectation value of the operator O in some arbitrary state psi, right? So how can I write that? Well, that expectation value is this object, right? Now I have a set of eigenstates here, right? And since these are eigenstates, I know that if I take this outer product of each eigenstate and I sum over all of the eigenstates, what do I get? I get the identity, right? This is the completeness theorem. Right? So when I take the expectation value of some state, of the operator in some arbitrary state, what I can do now, right, is I can insert the identity, this resolution of identity. One second. I can insert one resolution of the identity here. And I can insert on a second resolution of the identity after this. And then I'll have a sum over I and j. Okay. So what will be the result now? Well, since phi is an orthogonal basis, I can always decompose my state psi in terms of this orthogonal basis, right? So what will be phi j psi? Phi j psi will be cj, right? And what will be psi phi I? It will be ci star, right? So the result of this expectation value will be ci star oij cj, right? And there is another way in which I can write down these C's, right? Which is what? If I want to write it in terms of projectors. Well, I can write down a projection operator associated with each one of these eigenstates, right? This is my projection operator, right? So my expectation value of this state can also be written as a sum over these projection operators, right? So what happens in any measurement is that we are basically acting upon the state with these projection operators, right? And then we are taking the expectation value of that, of the result of that action. So coming back to this, to what I was talking about in terms of superdense coding, is that I have Bob here, and Bob is measuring some operator, right? And now the question is that what is that operator, right? So the operator is defined in terms of some matrix elements, right? So here, for instance, these are the matrix elements, right? Oij is phi I, O phi j, right? And phi I, phi j is the basis in which the measurement is being made, right? Alternatively, one can say that let's say that you have two different sets of basis vectors. Okay. Again, for lack of imagination, I'll just call them phi and phi prime. So in particular, in the case of superdense coding, for Alice, this would correspond to the computational basis. And for Bob, this would correspond to the Bell basis. Right? So what do we mean when we say that Bob makes a measurement in the Bell basis, right? Is that Bob has a set of 4 projection operators. Right? And if you take the sum of these projection operators, what do you get? You get the identity. And so what Bob does is he takes the state that he gets from Alice and acts on it with these projection operators, right? And then he takes he measures the probability of this projection operator, basically. Or, well, so sorry. So what Bob does is he measures the probability of this this projection operator, right? Like this. Okay. What is this probability going to be? We'll put a hat over here. This is going to be 1 if psi is equal to beta xy and 0 otherwise. Right? So you can convince yourself that this is the case. And these operators, each one of these operators is Hermitian. You can see that by definition. If you take the Hermitian conjugate of this, you will get the operator again, right? So each one of these projection operators is a Hermitian operator. So you can, so one can just take the expectation value of a projection operator, right? And if it's 1, that means the state that Alice sent to Bob was precisely the one which corresponded to this state. Otherwise, you get 0.
So like worst case, he'll have to do it 4 times. Is it?
Yeah, no, there is that. Well, yeah, no, that's correct. That he will have to do it 4 times. So what he can do is, right, he can just do this measurement, perform this measurement instead, right? Again, but this measurement will also not give him information. Yeah, no, you're right. That yeah, there's some issue. I will have to come up with a slightly better explanation of what's going on. Because of course, if you have to make 4 measurements, then that sort of defeats the purpose, right? Of using this protocol to transfer any kind of information. Okay. So I will look up that information in a little more detail and talk to you about it to you in the next class. Okay. And I apologize. Today's lecture was a little bit incoherent due to my own lack of preparation. But I promise you that the other 2 lectures will not be the same. Okay. Now, are there any questions?
Sir,
Yeah.
sir, for transmission, always required for EPR state?
Sorry, what?
For transmit some data to Alice to Bob, always required EPR state, entanglement state.
Well, I mean, yeah, I mean, that's the whole point, right? That if you want to use quantum correlations, right? So if you want to use quantum mechanics, how do you do that, right? You have to take some property of the 2 systems, some aspect of the 2 systems, between which there are some quantum correlations. Right?
Yes.
And then one party makes a change to one part of the system, right? And the reason that it can be used to transfer information from one to the other is because there are some quantum correlations. If there are no correlations, then making some change to one part of the system will have no effect on the whole system, right? It will only affect this
Yes,
subsystem. But because there is entanglement, it affects the global state. Right? And so then the second party can perform some other operations on that global state and conclude from that measurement, right? What was it that was done by the first party?
Yes.
So to give you an analogy, imagine that you and your friend are sitting in 2 different rooms, and one game that many children like to play is to you take a cup, you take a paper cup, and in the base of the cup you make a small hole, and then you take a piece of string, right? And then you put a knot around one end and you put it through that cup, and then you put the other end through the hole of that other cup, right? So you create a string, and there are 2 cups at either end. And when one person speaks into the cup, right, it is amazing that just that connecting string is enough to transmit sound, right? So you can be in different rooms and you can whisper into one of the cups and the other person will hear what you're saying. Have any of you played this game? Have any of you played this game by any chance?
No, sir.
No. Okay. So the situation is somewhat similar, right? It is because you have this string connecting the 2 systems that some information can transfer from one to the other. So the presence of entanglement between 2 parts of a system plays the role of a channel connecting those 2 parts.
Yes.
Okay. Any other questions? All right. In that case, I'll stop the recording.